So let's look at the first problem here. So we want to solve the linear system 6x1 minus 4x2 plus 8x3 plus x4 equals negative 8. Then we have here 3x1 minus 2x2 plus 4x3 equals 7. And then x2 plus x3 equals negative 2. So what we're going to do is to start with the augmented matrix. So here we will have 6, negative 4, 8, 1, negative 8. And then we have 3, negative 2, positive 4, and 7. And then 1, 1 here. So 0 here, 0 here. By the way, 0 here. And then we have negative 2. So from this augmented matrix, what we're going to do is to find the reduced row echelon form. And then once we have the reduced row echelon form, we can now um, give the general solution of this linear system. Okay. So when we do the reduction, okay, to reduce row echelon form, we will specifically write the row operations used, the elementary row operations used. So in the exam, you should also do that. Okay. So let's start with this. So we have 6, negative 4, 8, 1, and then negative 8. And then here we have 3, negative 2, 4, 0, 7. And then we have the 0 on the third row here. We have 0, 1, 1, 0, negative 2. So to do, we want to have a leading one, okay, on the top row, leftmost entry. But we have 6 in here. We can divide by 6, okay? We can divide by 6. But if we do that, what will happen is um, we will have some fractions. So as much as possible, to um, I want to reduce or I want to minimize the fractions appearing in here. So I'm not gonna divide this by 6. I mean, the first row, I'm not gonna divide it by 6. So what I'm gonna do is, well, I'll make this 0 now. Okay? I'll try to do something so that this will be 0. Okay? And for that, what we can do is to add, we can replace second row. Okay? We can replace second row by second row minus 1/2 first row. Okay? So second row minus 1/2 first row. And then we'll just copy the other rows. So for row 1, we'll just have 6, negative 4, 8, 1, and then negative 8. And then for row 2, we will have 3 minus 1/2 of 6. So 3 minus 3. Okay? 3 minus 3, that will be 0. Then here you have negative 2 minus 1/2 of negative 4. So this becomes negative 2 plus 2. So that will become 0. In here, we have 4 minus 1/2 of 8. That becomes 4 minus 4. That's again 0. In here, we will have 0 minus 1/2 of 1. So, well, we have this fraction. Anyway, that's just fine. Then for this, we have 7 minus 1/2 of negative 8. So this will become 7 plus 4. So this is 11. Then for the third row, we just copy 0, 1, 1, and then 0, negative 2. Okay? So from here, well, we can multiply the second row by 2 or negative 2. So we will get rid of this fraction. Okay, we can do that. We can also first interchange rows 2 and 3. So because this one here, it's already 0, this cannot be a leading one. But here we have here 1. We have a leading 1 in here. So um, we interchange them. Okay, we interchange them. So let's interchange first. We have row 2 interchange with row 3, and then we will have 6 minus 4, 8, 1, then negative 8, then 0, 1, 1, 0, negative 2, and then 0, 0, 0, negative 1 half, and then 11. Okay, and then we'll make this, we will multiply the third row by negative 2 to introduce the leading one on this row. Okay, so we multiply the third row by negative 2, so that we will have now, for the first row, we copy 6, negative 4, 8, 1, negative 8. For the second row, we also copy 0, 1, 1, 0, negative 2. For the third row, we multiply that by negative 2. So we will have this. So at this point, except for this leading entry here, which is not yet a leading one, we are on a row echelon form. Not completely in row echelon form because this is not a leading one, but we're almost there. Okay, so I will turn this later into a leading one. So we will proceed with step 6, meaning this is a leading one in here. I want to make everything above it 0. Okay, so we will have, for row 1, we will replace it by row 1 minus row 3. So row 1 minus row 3, we have 6, negative 4, 8. And then 1 minus 1, that becomes 0. And then here 8 or minus 8 minus negative 22. So that becomes minus 8 plus 22. And that's equal to 14. Okay. And then we copy row 2, 0, 1, 1, 0, negative 2. And then row 3, 0, 0, 0, 1, negative 22. And now if we divide row 1 by 6, we still have a fraction in here. So let's skip that. Yeah, let's skip that first. So what we're going to do now, since all the entries above this leading one here are 0, we now go to 1 row higher. So this is a leading 1. We want the term above it a 0. So what we can do is to add row 1 plus 4 row 2. Okay? So if we do that, we will have what? 6 plus 0, that's just 6. Negative 4 plus 4, that becomes 0. Then here you have 8 plus 4 times 1. Now that is equal to 12. And then 0 plus 0, that's still 0. And then in here you have 14 plus 4 times negative 2. So 14 minus 8, and that's equal to 6. Then here we have 0, 1, 1, 0, negative 2. And then third row, it's 0, 0, 0, 1, negative 22. And now there's one operation left, or there's one step to do. and that's to divide this guy here by 6 to introduce a leading one. So we just divide row 1 by 6. And we're lucky that everything here will be integer. So we will have 1, 0, 2, 0, 1, then 0, 1, 1, 0, negative 2, then 0, 0, 0, 1, negative 22. Okay? So remember, this is your x sub 1 column, x sub 2 column, x sub 3 column, x sub 4 column. So from here, what we will get is the following. We have x sub 1 plus 2x sub 3 equals 1. And then we have x sub 2 plus x sub 3, that's equal to negative 2. And then x sub 4, this is equal to negative 22. Okay? So this means the general solution is, so we let t be any real number, okay? And set x sub 3 be equal to that t, correct? So the general solution is we will have x sub 1, this is equal to negative 2t plus 1. So we put this on the other side. X sub 2, we will have minus t minus 2. Okay. We have x sub 3. This is equal to t. And then we have x sub 4. This is equal to negative 22, where t is arbitrary here. Okay. T is arbitrary. Okay. Any questions? Next problem. We have A, B, and C in here, and then we want to find B, A inverse plus C transpose A. Okay. So for the second, of course, we need to find the trace of BC minus 2I. So first, we'll have to calculate A inverse. So this is for number 1. We want to calculate A inverse, and this is your matrix A. A inverse, it's just 1 over the determinant of A. So that's 5 times negative 1 minus 2 or minus negative 2 times 3. And then what do? We interchange. So this will be negative 1, this will be 5, and then we negate these two guys here. So we have negative 3 and then positive 2. Okay? And then on here, we have negative 5 plus 6. So the determinant of A, it's just 1. So this will just be negative 1, 2, negative 3, 5. Okay? So now, let us calculate BA inverse plus C transpose A. So matrix B, it's 1, 2, 0, negative 1, negative 2, 1. Then we multiply this to -1, 2, -3, 5. So that's your BA inverse. Then plus C transpose. So we transpose this guy here. So this will be 3, 1, -3, 2, and then 2, -1. And then multiply to A, which is this. We have 5, -2, 3, -1. Then let's do the multiplication. So for the first one here, we have 1 times -1. So that's -1 plus 2 times -3. That's -6. And then for this, we have 0 times -1 plus -1 times -3. That's +3. Then here you have -2 times -1. That's 2. Plus 1 times -3. That's -3. And then for this column here, we have 1 times 2. That's 2. Then 2 times 5. That's 10. And then here 0 times 2. That's 0. -1 times 5. We have -5. And then we have -2 times 2. That's -4. Then 1 times 5. That's +5. So this is BA inverse. Then let's have C transpose A. We have 3 times 5, that's 15. And then 1 times 3, so that's +3. And then -3 times 5, that's -15. Plus 2 times 3, that's 6. Then here you have 2 times 5, that's 10. Plus -1 times 3, that's -3. Then for the second column here, we have 3 times -2, that's -6. 1 times -1, that's -1. -3 times -2, that's +6. 2 times -1, that's -2. Then 2 times 3, that's, where am I? So -3 times -2, that's +6. 2 times -1, that's -2. So 2 times -2, that's -4. -1 times -1, we have +1. Okay? Okay? So if we add this, so basically you're just going to add the first entry here with the first entry here. So that's just adding all these numbers with these numbers. Okay? So we will have -1 plus -6, that's -7. Okay? Plus 15, that's 8. Plus 3, that's 11. And then here 2 plus 10, that's 12. Minus 6, that's +6. Minus 1, that's +5. In here we have 3 minus 15, that's -12. Plus 6, that's -6 here. Then -5 plus 6, that's 1. Minus 2, it's -1. And then for this, we have 2 plus -3, that's -1. Plus 10, 9. Minus 3, that's 6. And then -4 plus 5, that's 1. -4, that's -3. Plus 1, that's -2. So this is the answer for BA inverse plus C transpose A. So this is BA inverse plus C transpose A. Let us work on the second problem for this item. We want to find the trace of BC minus 2I. So first, let us calculate BC. So BC, we have this 1, 2, 0, negative 1, negative 2, 1. That's for B. Then for C, we have 3, negative 3, 2, 1, 2, negative 1. So if we multiply this, we will have um, 1 times 3, that's 3. Then 2 times 1, that's 2. Then 1 times negative 3, that's negative 3 here. 2 times 2, that's 4. Then 1 times 2, that's 2. 2 times negative 1, that's minus 2. Okay? And then we will have 0 times this first entries here. They will just be 0. So 0 times 3, that's 0. Plus negative 1 times 1, we will have negative 1 in here. And then 0 times negative 3, that's again 0. So here negative 1 times 2, that's negative 2. And you expect this one to be positive 1. Okay? Then finally, we have negative 2 times 3, that's negative 6. 1 times 1, that's 1. So it's negative 6 plus 1. Negative 2 times negative 3, that's positive 6. Plus 1 times 2, that's just 2. Then here, negative 2 times 2, that's negative 4. Plus 1 times negative 1, that's negative 1. So BC, this will be equal to, so 3 plus 2, that's 5. Negative 3 plus 4, that's 1. 2 minus 2, that's 0. Okay? And then we have negative 1, negative 2, 1. Then we have negative 5, 8, and then negative 5. So this is BC. Okay? And then we add or we subtract 2I. So we have a 3 by 3 matrix in here. So if we get the identity, it's just 2I. So we have here the trace of BC minus 2I. So this is equal to the trace. Let's write this. You have 5, 1, 0, negative 1, negative 2, 1, negative 5, 8, negative 5. So minus 2 times the identity. The identity, it's just 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So this is just the trace of, let us calculate. The one that will change only is the diagonal or the diagonal entries. Because this one is 0, this one is 0. So you can just copy the other entries. So in here, you will have 5 minus 2. Okay, that's 3. And then minus 2, minus 2. So this middle part here, minus 2, minus 2. That's minus 4. Then here, minus 5, minus 2. That's minus 7. And for the rest, you'll just copy that. Okay. And therefore, the trace, you just add the diagonal entries. So this is now equal to 3 minus 4 minus 7. This is equal to minus 8. So this is the trace of BC minus 2I. Okay? Next problem here. So we want to find the values of P so that capital M is not invertible. Okay? So we have a lot of ways to determine whether this matrix M here is not invertible. We have 7 equivalent statements. So what we're going to do is to use the determinant equivalent statement. So this matrix M will not be invertible if the determinant of M is equal to 0. So we'll just solve for P such that the determinant of this M is equal to 0. So that's for the first problem. For the second problem, when P equals 0, we determine the conditions for B1, B2, and B3 so that this matrix equation here is consistent. So let's do number 1. We first find the determinant of M. Okay, so we have 2 or 3 or several methods to find the determinant, but we'll use the shortest way. We have here 3 and then 6 minus P and then P squared, then 1, 2, 0, then 0, 1, negative 1. And then we augment the first 2 columns, 6 minus P, 2, 1 for this column. And then we do this, okay? So we multiply the entries here, we multiply the entries here, and then the entries here. So for this, we have negative 6. Of course, this guy here is 0. And then here you have P squared. And then for the going up, this guy here, this guy here, and this guy here. So for this guy here, we have 0. Also here 0. And then here we have 6 minus P. In fact, it's negative of 6 minus P. So the determinant of M, this is equal to negative 6 plus P squared minus the quantity of 0 minus, I'll just put that as 0. So 0 minus quantity 6 minus P. So if we simplify this, we will have negative 6 plus P squared plus 6 minus P. Okay? Minus minus here, they will cancel each other. It becomes plus. So we have this. So if we simplify this further, we will have P squared minus P. Okay? So M is invertible or is not invertible. Okay? If determinant of M, and this is equal to P squared minus P, if this is equal to 0. Or we have what? P times P minus 1 equals 0. Or we have P equals 0 or P minus 1 equals 0. Or finally, P equals 0 or P equals 1. So these are the values of P for which this matrix M is not invertible. For the second problem, for P equals 0, determine the conditions for B1, B2, and B3 so that the matrix equation is consistent. So for number 2, let P be equal to 0. Then M, this is just what? 3, 6, 0, 1, 2, 0, 0, 1, negative 1. Okay? So, mx plus b. Let's just get the augmented matrix. So we will have 6 or 3, 6, 0, 1, 2, 0, 0, 1, negative 1. We augment this to b1, b2, b3. So in here, we clearly have, we can interchange these two guys here, this and this. Okay, so if we do that, we will have, so we interchange row. Actually, let's just interchange row 2 and row 3. Okay, so we interchange row 2 and row 3. Okay, we interchange row 2 and row 3, so we keep this. This is b1, and then we have 0, 1, negative 1, b3, then we have 1, 2, 0, b2. And then from here, we'll subtract. Okay, we'll do row 3 minus 1/3 row 1. Okay, and what will happen is, so let me just adjust this guy here. So what will happen is, so we just copy row 1, it's still 3, 6, 0, b1. Row 2, we have 0, 1, negative 1, b3. And then row 3 minus 1/3 row 1. So you will have here 0. You will also have 0 in here. And then 0 in here. And then the last entry here will be b2 minus 1/3 b1. Correct? Okay. And then if we continue with this, we can make this 0. And we will have an almost reduced row echelon form. But the third row here, we have the left-hand side to be 0. Right-hand side is b2 minus 1/3 b1. Okay? But this means this matrix here, matrix equation here, okay, will be consistent if this guy here is equal to 0. Okay? So we need, for M, let me just write this as mx equals b. So for this to be consistent, for mx equals b to be consistent, okay, we need, so one needs b2 minus 1/3 b3 or minus 1/3 b1 to be 0. Okay? Or we need our b2 to be 1/3 b1. So the conditions are, so the conditions are, we need, we can have b1 and b3 to be any real number, but your b2, it must be 1/3 b1. So this is the conclusion. Okay? Questions? Next, find the inverse of n. We are given this n. Find the determinant of n. And then in here, using parts A and B, so using actually part 1 and part 2, find the cofactor entries C11 and C31. So let's start with the first one. We want to find the inverse of n, and we'll do that using inversion algorithm. So we have the matrix n 0, 0, 1, 0, 0, 1, 0, 3, 1, 0, 2, 0, 0, 0, 0, negative 3. And then we augment the identity matrix. Okay? We augment the identity matrix. So I'll just write the identity matrix using blue ink here. 0, 0, 1, 0, 0, 0, 0, 1. Okay? So the leftmost entry in here with non-zero number, it's this guy here. All the rest are 0, so we can just interchange row 3 and row 1. So if we do that, we will have 1, 0, 2, 0, and then in here we have 0, 0, 1, 0. For the second, in here, we'll just copy. So 0, 1, 0, 3, 0, 1, 1, 0, 1, 0, 0. Excuse me. And then we'll get row 1. We'll have 0, 0, 1, 0, 1, 0, oops. So 1, 0, 0, 0. And then we'll just copy row 4. 0, 0, 0, negative 3, 0, 0, 0, 1. Okay? And then what's next? We can divide this by 1/3. Okay? We can divide this sorry, we can divide this by negative 3, okay, to introduce a leading one, okay. But before doing that, what I want to do is to make this a 0 entry, okay. And in order to do that, we'll just have to add row 2 plus row 4, okay. So row 2 plus row 4, I'll have here 1, 0, 2, 0. And then on the other side here, I have 0, 0, 1, 0. Then row 2 plus row 4, I'll have 0 plus 0, that's still 0. 1 plus 0, that's still 1. 0 plus 0, that's 0. 3 plus negative 3, that's 0. Then in here, I have 0 plus 0, that's again 0. 1 plus 0, that's 0. Sorry, that's 1. 0 plus 0, that's 0. 0 plus 1, that becomes 1. Then row 3 will just copy 0, 0, 1, 0. 1, 0, 0, 0. Row 4 will also copy. We have 0, 0, 0, negative 3. And then here 0, 0, 0, 1. Okay. And then now we're ready to make this a leading one. Okay. And at the same time, I will make this 0. Okay. And by doing those two steps, we'll have the identity on this side. And therefore, we will have the inverse on this side. So we will have row 4 divided by negative 3. And then row 1 minus 2 row 3. So for this, we have 1, 0. Okay, so 1 minus 2 row 3, that's 0, 0 minus 0, and then 2 minus 2 times 1. So that becomes 0. And then 0 minus 0, again 0. And then we have 0 minus 2. Okay, so that will become negative 2. And then 0 minus 0, that's still 0. 1 minus 0, that's 1. And then 0 minus 0, that's 0. And then for the second row, we'll just copy. The third row will also copy. So copying, we have 0, 1, 0, 0 here. Here we have 0, 0, 1, 0. On the other side, we have 0, 1, 0, 1. And then 1, 0, 0, 0. For the fourth row, we divide by negative 3. So we will have 0, 0, 0, 1. Then 0, 0, 0, and then negative 1/3. Okay? Okay. So we have this. So N inverse. Therefore, N inverse, this is equal to the matrix, this guy here. So we have negative 2, 0, 1, 0. Then 0, 1, 0, 1. 1, 0, 0, 0, 0, 0, 0, negative 1, third. So this is our N inverse. Okay. Next, we want to find the determinant of N. So from here, okay, we can just do expansion, and we expand along the first column. You can also expand along the first row, okay? But anyway, I'll expand along the first column. So determinant of N. So in here, I have 0, and there I have 1 times negative 1 raised to, this is 1, 1, 2, 1, 3, 1. So negative 1 raised to 3 plus 1. And then I need the determinant. So I am at this entry. I'll remove this, I'll remove this. So I'll get the determinant of 0, 1, 0, 1, 0, 3, 0, 0, negative 3. Okay? And then, well, negative 1 raised to 3 plus 1, that's just positive 1. So I'm just trying to get the determinant of this. And if you calculate this, we can still do expansion along the first column or along the first row. It's up to you. Yeah, let's just do expansion along the first row this time. So I am expanding, okay, here. So cofactor expansion along the first row, okay? So I am at this point. So remove this and then remove this. I will have 1 times negative 1 raised to, this is 1, 1 entry, this is 1, 2 entry. So raised to 1 plus 2. And then the determinant of 1, 3, 0, negative 3. So again, this guy here, it's just positive 1, so it disappeared. For this guy, it came from the determinant of this 3 by 3 matrix. And then 1 times negative 1 raised to 1 plus 3. This is negative 1. So this will be equal to negative of, in here, we'll just have negative 3 minus 0. So this is equal to positive 3. So this is the determinant of N. Okay? So this is for your number 2. For number 3, we use the results of part 1 or part 2, okay, to find the cofactor entries C11 and C31. Now look, you have the determinant in part 2. You have the inverse in part 1. Okay? Which means we can get the adjoint of N. Okay? So by parts 1 and 2, adjoint of N, this is equal to the determinant of N times N inverse. Okay? in our lecture, the original formula that was given to you, it's A inverse equals 1 over determinant of A times adjoint of A. That's the formula that was given to you. So we can manipulate this and we will get this equation. Therefore, what is the adjoint? This is equal to 3. That's your determinant. And then we copy. Okay? And then this matrix here. This is your N inverse. So let me just copy this. Okay. So we have this. And therefore, we'll just have negative 6, 0, 3, 0, 0, 3, 0, 3, 3, 0, 0, 0, 0, 0, 0, negative 1. This is the adjoint. And therefore, this guy here, this is your C1, 1, and 3. And then this is your C3, 1, and 3. Remember, the adjoint, it's the transpose of your matrix of cofactors. Okay? So therefore, C11, that's equal to negative 6. And then C31, that's equal to positive 3. Okay? Question? Next problem. We use Kramer's rule to solve for x sub 4. So pardon this spelling here. So let me change this. Okay. So Kramer's rule. Oops. So we are only interested with the fourth variable. So let us write. Say our matrix A, it's the matrix of coefficients here. So we have 4, 1, 0, 0. Then 0, 1, negative 3, 0. Then 10, 0, 1, 1. Then 0, negative 1, 1, 0. So this is our matrix A. Our matrix B, it's the constant vector here. We have 4, 1, 0, negative 3. And we will need A sub 4 because we want X sub 4. So A sub 4 in here, let's just write it. It's the same matrix in here except that we replace the fourth column here by this matrix B. So we will have 4, 1, 0, 4. and then 0, 1, negative 3, 1, and then 10, 0, 1, 0, and then 0, negative 1, 1, 0. Okay? Therefore, if determinant of A, this is not equal to 0, then x sub 4, this is simply determinant of A sub 4 divided by determinant of A. Okay? Okay. So, let's see. Let's find the determinant of A. We can do the expansion along this fourth column. It has plenty of zeros. Okay. So let's see. We want the determinant of A. This is equal to. So we are expanding along this column here. And we will use this guy here because anyway, this is 0 and 0 and 0 in here. So we'll just have this. And then we'll delete this row and this column. So we will have 1 times negative 1 raised to, so this is 1, 4, 2, 4, and then 3, 4 here. Okay, so negative 1 raised to 3 plus 4, and then we want the determinant of the matrix here, 4, 1, 0, 0, 1, negative 3, 0, negative 1, 1. Okay? Okay? So there was a correction here. Yes, this should be negative 3. You are right. So let me just change that. Thank you for noticing that. So this is negative 3. So anyway, we proceed with the determinant of A. Negative 1 raised to 3 plus 4, that's negative 1. So we'll just have negative 1 or negative. And then we can do expansion also, cofactor expansion to determine the determinant of this. You can do the other method, but I think it will be easier if we use the cofactor expansion, because if you look at the first row, the first column, there's only one entry which is non-zero. So it's nice to use that. So for this, we do this expansion here. And then, of course, if we get this entry here, we delete this and then this. And therefore, we will have 4 times negative 1 raised to 1 plus 1. That's the 1, 1 entry here. And then determinant of 1, negative 3, negative 1, 1. Which means this is just negative 4 times 1 minus, so this is 1 times 1, that's 1, minus negative 1 times negative 3, so that's positive 3. Which means we will have negative 4 times negative 2, that's equal to negative 8. This is the determinant of A. Yes, it should be positive 8. Thank you. So it's positive 8. So again, we want to find the determinant of A sub 4, and we are expanding along the first column. Okay? At this first column, so cofactor expansion, we get this entry. Okay? That's your 4. This is the 1, 1 entry. And then we need to get the determinant of the submatrix after deleting the row and the column where your entry belongs to. That's why you are at 4, you delete this first row here. And then you also delete this column here. So you'll be left with this submatrix here. Okay? And then of course this is 0. So 0 times whatever, it's just 0. And then here you have 10. That's why you have this 10 here. And then negative 1 raised to 3 plus 1, because this 10 here, it's the 3, 1 entry. And it's the 3, 1 entry, you delete the third row and the first column. That's why we have deleted this part and also this part, and we have this submatrix here. 1, 0, 4, 1, negative 3, 1, negative 1, 1, negative 3. And then we just calculate for the determinant. Okay? For this guy here, we'll do again cofactor expansion. I'll do the expansion along this second row. Okay? So if we do that, this is still equal to 4. Negative 1 raised to 1 plus 1, that's positive 1. And then here, this is the entry. So we have 1 times negative 1 raised to. What is the entry? On which location? What is the location of this entry? It's the 2, 2 entry. So you have 2 plus 2 as an exponent here. And then you delete this because you are now doing this entry. You delete this. You also delete this. And therefore, we have here 1, 1, negative 1, negative 3. Okay? And then we do the determinant here. Okay? So we have plus 10, negative 1 raised to 3 plus 1, it's just positive 1 again. And then for this, we can do cofactor expansion again in the row 1. Okay? So we are expanding along this row. So we start with this one here. We have 1 times negative 1 raised to 1, 1, or 1 plus 1. So that's the 1, 1 entry. And then determinant. You delete this row, you delete this column. So you'll be left with negative 3, 1, 1, negative 3. Okay? So that's for this guy here. And then for this guy, because this one is 0, so we can skip this part here. For this guy, we have plus 4 times negative 1 raised to, the entry location is 1, 3. So this is 1 plus 3. So we delete the first row and then the third column. we'll now have to get the determinant of this submatrix here. 1, -3, -1, 1. Then you close the parentheses. And then you solve all these determinants. These are all 2 by 2 matrices now, so you can easily get the determinants. So in here, we will have 4. This is 1 times 1 again. So it's just 1. For this, we have 1 times -3. That's -3 minus -1 times 1. So minus -1 there. Plus 10 times the quantity. So we are now at this part. This is just 1. -1 raised to 1 plus 1. That's positive 1. And times 1. That's again 1. So we'll just have the determinant of this. The determinant will be -3 times -3. That's positive 9. Minus 1 times 1. That's 1. Then plus, here you have 4. And then -1 raised to 1 plus 3. That's again 1. And then we get the determinant of this. It's 1 times 1. That's 1. Minus -1 times -3. That's 3. And then close parenthesis. So just clearly put the grouping and put that correctly. Put them correctly. So what will this be? Here we have -3 plus 1, that's -2. So 4 times -2, that's -8. Plus this guy here, 4, what is this? 1 minus 3, that's -2. So 4 times -2. So let me write it here. So this guy here, 4 times -2, that's -8. And then for this, we just have 8, correct? So you have here 8 minus 8. And that's 0. Times 10, it's still 0. So this guy here, this is just -8. Okay? Therefore, we can now have x sub 4. So let me write the final answer here. So x sub 4, this is equal to the determinant of a sub 4 over determinant of a. This is -8 for the determinant of a sub 4 over the determinant of a, that's positive 8. So this is equal to -1. Okay? Questions? Okay. Next, let A be a square matrix such that a to the 4 equals 0. Find the inverse of 1 minus A. Prove your claim. So here we have a hint in college algebra. The polynomial 1 minus x to the n can be factored into this expression. Okay? So for this, we let p of x, this is equal to 1 minus x to the 4.
And according to this guy here, this is equal to 1 minus x times 1 plus x squared plus x cubed. Okay? So, you have P of A. This is equal to 1 minus, or I, sorry, that should be I, minus A to the 4. Take note that we are evaluating a matrix here. So the number 1 here, it becomes your identity matrix. And according to this, we'll just have I minus A times I plus A squared plus A cubed. But A to the 4, it's equal to 0. Okay? A to the 4, it's equal to 0. Since A to the 4, this is equal to 0, we'll just have 1 or I minus A times I plus A squared plus A cubed. This is just equal to I. Correct? Because A to the 4 here, it's just 0. And now, you see clearly that this is the inverse of this guy here. Okay? So, the inverse. So, I minus A inverse, it's just this I plus A squared plus A cubed. And that's it. Questions? Next, let's have here true or false. So for each statement, write true if it is always correct, otherwise write false. So the first, a linear system whose equations are all homogeneous must be consistent. So is this true or false? Anyone?
True.
Yes, that is correct. Thank you. So the answer here is true. So if the equations are all homogeneous, the linear system itself is homogeneous. And we know if you have a homogeneous linear system, the trivial solution is always a solution. Okay? So this is true. Next, if an elementary row operation is applied to a matrix that is in row echelon form, then the resulting matrix will still be in row echelon form. True or false? If an elementary row operation is applied to a matrix that is in row echelon form, then the resulting matrix will still be in row echelon form.
False.
Correct. So the answer is false. If you switch two rows, then definitely you will not get a row echelon form. So this is false. Now, for number 3, if A and B are square matrices of the same size, then AB equals BA. True or false? That's false. Thank you. So yes, it is false. Number 4, if M is a square matrix whose minors are all 0, then the determinant of M equals 0. True or false? True or false? The answer is true. Correct. Okay? Remember that the cofactors, they are coming from the minors also. So if the minors are 0, then the cofactors are all 0. So if you use your cofactor expansion, you add all the zeros. Determinant is equal to 0. Now, if A is a square matrix and the linear system AX equals B has multiple solutions for X, then the determinant of A equals 0. True or false? True or false? The correct answer here, this is true. Take note that your A here, it's already a square matrix, so determinant can be defined. Okay? And you remember the equivalent statements? If your system has a unique solution, determinant must not be equal to 0. But that's for the unique, and they are equivalent. So if the solution is not unique, or if the system has more than one solution, determinant must be equal to 0. So this statement here, it's true. And number 6, it's actually the same, except that we have here 0. So we'll just copy. So this is for any column matrix B. And here you have the 0 column. So they also mean the same thing. Okay? So that's for the true or false question. Let's look at this. If A is a square matrix such that its reduced row echelon form is the identity matrix, then A is invertible. So we want to prove this statement here. So, proving part. Okay? So, how do we prove this? Proof. So, let A be a square matrix. Let A be a square matrix. Okay? Then, if this is a square matrix, well, any matrix will have this. But here, we can find. Then there exists a sequence of elementary matrices. So we have here, so a sequence of elementary matrices. Elementary matrices. Let's name that. You have E1, E2, until, say, EK. Such that if you multiply all of these and then with A, you'll get the identity matrix. So here, you apply the elementary row operation on A, and then you apply again another elementary row operation, and then you do this until you have this, and eventually you will get the identity matrix. Okay? Now, elementary matrices are invertible. So now, elementary matrices are invertible. Elementary matrices are invertible. And so, the product or their products is invertible. So their product is invertible. Okay? And if it is invertible and you multiply it to A, okay, this guy here, it's invertible. You multiply it to A and you get the identity matrix. Remember that theorem? A must be invertible. Okay? Therefore, okay, here, therefore, EA equals I implies, so let me write what E here is, where E, it's just this product here, EK until E2, E1. Okay, where we have this implies A is invertible. So we have proved the statement. So as you can see, 3 sentences, actually 4. Well, I added this first line here. Okay. Okay. Prove. Suppose A is an M by N matrix. So A is not necessarily a square matrix. Suppose also B is an N by M matrix. So again, B is not necessarily a square matrix. And such that the product BA, it's the identity matrix. Okay? If for some m by 1 matrix or m by 1 matrix B, the equation AX equals B has a solution, then this solution is unique. Okay? So we are assuming that this has a solution. We want to prove that the solution is unique. And then once we prove that it is unique, we identify what the unique solution is. Okay? Now, look at this. Your B, this is what? An N by M. Okay? Matrix. Your A, it's an M by N. So if you multiply this, you will get an N by N matrix. That's why, if you look at this, the subscript is N. The subscript here, we put it because, well, there is M also in here. Okay? And then, if for some M by 1 matrix, the equation AX equals B has a solution. So we look at that. Your A, this is M by N. And then your matrix B here, this is M by 1, which means, of course, you have the column vector X. It consists of your variables. This should be N by 1. Okay? But it, well, should be automatic. But if you multiply these two, you will indeed get M by 1 matrix. Okay? So all of these things here make sense. Now, we want to prove that if AX equals B has a solution, then this solution is unique. So let's prove that. So proof. Okay. So using the assumption, suppose we have two solutions. Suppose x1 and x2 are solutions of the equation AX equals B. Then, of course, if they are solutions, the equation must be satisfied. So AX1 equals B, AX2, this is also equal to B. Okay? Now, since BA, this is equal to the identity matrix, okay? You will have this, 0, okay? Let's start with the left-hand side. So I'll not start with 0 in here. You will have here x sub 1 minus x sub 2. This is equal to I, that's your identity matrix, multiplied to x sub 1 minus x sub 2. Correct? But your IN, that's your BA. So you can replace the IN by BA. X sub 1 minus x sub 2 in here. And then we can distribute the A over this difference. So this will be equal to B times AX1 minus AX2. But look at this. AX1, that's equal to B. AX2, that's also equal to this B here. So this will just be B times small b minus small b. And this is just B times the 0 vector, which is just the 0 vector. Okay? So, x1 minus x2 equals the 0 vector, or x1 equals x2. So, whatever two solutions, quote unquote, whatever two solutions you get, okay, you will end up with getting the same solution. So, the solution is unique. Okay? Now we want to identify the unique solution. Okay? For the unique solution, for the unique solution, okay? For the unique solution, so say that's your x1. Again, this is in x1, but this is, again, the in, that's BA. BA x1, but AX1, that's equal to B. So this is now equal to B times the vector B. So the unique solution has this form. Okay? Any questions? Let's have this last problem. If the entries in each row of an n by n matrix, take note of this, if the entries in each row of an n by n matrix A add up to 0, then the determinant of A is equal to 0. Okay? So again, if the entries in each row of an n by n matrix A add up to 0, then the determinant of A is equal to 0. So proof. So let's just have A here be the matrix. So we need an n by n matrix. So A11, A12 until A1n, A21, A22 until A2n. We do this, we have AN1, AN2, and then we have ANN. So let this matrix be our n by n matrix, such that according to this, each entries the entries in each row add up to 0. So you have A11 plus A12 plus until A1n, this is equal to 0. A21 plus A22 plus until A2n, this is also equal to 0, until you have AN1 plus AN2 plus until ANN, this is equal to 0. This is the assumption. We want to prove that the determinant of A, it is equal to 0. Now, there is a hint here. Consider the product AX where X is an n by 1 matrix, each of whose entries is 1. Okay? So, here's what we're gonna do. Consider the homogeneous linear system. Homogeneous linear system. AX equals 0. Okay? Then the 0 vector, then the 0 column vector is a solution. So the 0 column vector is a solution. The 0 column vector, it's your trivial solution. Okay? Now, take x sub 1 to be the vector, okay, whose entries are all 1. That's your hint. And let me write the dimension, of course, n by 1. Okay? Then, what do we have? Let me just put the continuation here. Then, a x sub 1, this is equal to, you have the matrix A11, A12, until A1n, etc. You have AN1, AN2, until you have ANN. That's your matrix A. Your matrix X1, you have 1, 1, until you have 1. But you have what? If you do the multiplication in here, you just have A1, 1 times 1, plus A1, 2 times 1, that's A1, 2, plus you continue, you will have A1n. Same is true with your second row here. Okay? And you continue that, you will have until the last row, you have AN1 plus AN2 plus until ANN. And notice, according to this is 0. This is also 0 here. And everything will be 0. So what does this mean? X sub 1 is also a solution of this system. So x sub 1 is a solution of AX equals 0. Now you got two solutions, your x sub 1 and the trivial vector. So the system has at least two solutions. So AX equals 0 has at least two solutions. Has at least two solutions. And therefore, the determinant of A must be equal to 0. And therefore, determinant of A, this must be equal to 0. And that's the end of the proof.